Hello and welcome to part 1 of our video where we're going to be looking at the past paper questions from the topic Particle Model of Matter. Download the booklet from the link below, have a go at the questions, then come back and see how well we've done with those answers as we go through it. So let's get started. So we're going to be looking at the first part of the particle model of matter. Start straight off with a 6-mark question. So in this question, it tells us that a student removes a material from a freezer and heats it up. They use a heater with a constant power output. They then plot a heating curve of the material as its temperature rises. We need to describe and explain what the graph tells us about the material being heated. So when we're looking at the 6-mark question, we're going to break it down into 2 parts. First, we need to describe what's happening, and then we need to explain what the graph is telling us. So let's take a look at this graph. What do we notice first of all? Well, we can see that we've got our temperature up here, and we can see we've got time along the axis here. We can see that over time it's heating up, and we can also see that these 2 points where it levels off, this point here and this point here. Therefore we know these are where our state changes are happening. As it's at its coldest here, we know that the substance must be a solid. Therefore, as it heats up, it's going to turn into a liquid at these points and a gas up here. We therefore know this point here, where the temperature is constant, is changing from a solid to a liquid, where it's melting, and here where it's going from a liquid to a gas, it's boiling. So, what can we describe about this graph? Well, firstly, we can see that it's showing us the 3 states of matter of this material: the solid, the liquid and the gas. We can also tell that it's not water. Again, this is the only substance we're expected to know. Obviously water would melt at 0 and would boil at 100. Other things we could describe about it is what it's like at room temperature. So room temperature is roughly around about 20 or just over 20, and we can see if we come across, it would be a liquid. What other points could we make? Well, we could start to explain some of these points here. So we know that it melts at minus 10 degrees Celsius. We know that it boils at 90 degrees Celsius. Therefore, we know that at any temperature below minus 10, it will be a solid, and at any temperature above 90 degrees, it will be a gas. And finally, we know therefore it will be a liquid between minus 10 and 90 degrees Celsius. Here we can see we've got 6 clear points getting us 6 marks. Let's move on to question 2. In question 2, it shows us that a scientist completes an experiment to determine the specific heat capacity of water. She uses an immersion heater to increase the temperature of the water in the beaker. Suggest 2 ways to ensure the scientist obtains accurate results. There's a whole range of different things that we could pick here, but there's some really common ones. Number 1, we want to reduce any heat loss to the environment, so we could use insulation. We also want to make sure that all of the energy from the immersion heater goes into heating the water and not the air around it. So we could also ensure that the immersion heater is fully submerged in the water. There are many other answers we could give. For example, we also want to make sure that the temperature of the water is constant throughout, so we could stir the water. Okay, let's move on with those questions. Is there a random error in this experiment? Explain your answer. We're not going to get a mark for the yes or the no, because it's only 1 mark, but the answer here is no. And the reason there's no random error is because you can see these are very clearly in a clear line, all close to the line of best fit. So our answer is a clear line, all points are close to the line of best fit. The scientist thinks that the points labelled B on the graph is an anomaly. Is she correct? And explain your answer. Well, B seems to have disappeared off my labelling. I'll make sure it's added up. So B is this one here. So is this point an anomaly? Well, it doesn't lie on my line of best fit. However, you can see it's really close to the line of best fit, and it also again follows the pattern. So no, point B is very close to the line of best fit, and therefore it's unlikely to be an anomalous result. Okay, we're going to need our graph back. So for this one here, we want to calculate the gradient of the graph. Let's move it so we can get both into shot. So to calculate the gradient of the graph, we need to be working out our gradient, so we need to know our change in x divided by our change in y. Now we can clearly see that my point goes 0, 0. When we're trying to work out the gradient, it's best to choose 2 points that are as far away from each other as possible. So we're going to use the two extremes of my graph at the origin and right up here. So if I take this point here, I can see that my change in y from 0 to 8 is 8, divided by the change in x, and the change in x goes from 0 to 200, which is 200. So my gradient will be 8 divided by 200, which will give me 0.04. It also asks for the unit. Well, the units are told to us in the graph. So 8 was degrees Celsius, divided by 200, which was my time in seconds. So I was doing 8 degrees Celsius divided by 200 seconds, showing me my unit will be degrees Celsius per second. Like so. Okay, so question 2.5 is an equation question worth 6 marks. This indicates to me that I'm going to need to use 2 equations to work out the answer. So the scientist writes down more results. It gives us the mass of water used and the power of the immersion heater, and we need to calculate the specific heat capacity of the water. Well, firstly, I'm going to think about the equation that I'm going to use, which is this one here, that the change in the thermal energy equals the mass multiplied by the specific heat capacity multiplied by the temperature change. So let's see what numbers I can put in. I think I'm going to need my graph again. So again, let's take that extreme point over here. So this was an 8 degree temperature change. So my temperature change over here was 8, multiplied by the specific heat capacity, multiplied by the mass. Well, the mass it tells us in the question is 0.1, equals the change in thermal energy. Now this is the problem. I don't have the change in the thermal energy. So I need to use another equation to see if I can work that out. And the equation that I'm going to use is power multiplied by time equals the energy transferred. And in this example, assuming no energy loss, the energy transferred will be the same as the change in thermal energy. So my power is over here, 12.8, multiplied by the time. So to get to 8 degrees Celsius rise, took 200 seconds. So 12.8 multiplied by 200 is going to give me 2,560 joules, which I can put back over here. Now I just need to rearrange this equation. So I want to bring the 0.1 over here by dividing, and bring the 8 over here by dividing. So 2,560 divided by 0.1 times 8 will give me the specific heat capacity. If I work that out, I get 3,200 as my answer for the specific heat capacity. Now I need the units, and again, the units are hidden in the workings. So 2,560 was my energy transfer, that was in joules, and I was dividing it by 0.1, which was kilograms, my mass, multiplied by my degrees Celsius, my temperature, and there's my units, joules per kilograms, degrees Celsius. As I said, look out, a 6-mark question based on formula. You're always going to need 2 formula. Okay, let's have a look at question 3. So in question 3, 2 beakers are filled with equal masses of liquids X and Y at the same temperature. The beakers are allowed to cool and the temperature of the liquids are monitored over time. The graph shows the results. Using the graph, compare what happens to liquids X and Y at 55 degrees Celsius. Suggest what's happening to the liquid at this temperature. So again, flat lines. Okay, that's what we're looking at here. 55 is these flat lines. This is the point where state changes take place. So if we know it's a liquid, we know it's cooling down, therefore it's going to become a solid. So we know just what's happening to the liquid. This will be the point where they are freezing. We need to say why this is happening. So why do we know it's freezing? So this is because the temperature remains constant at 55 degrees Celsius. And because we're comparing, we also need to find a difference. And so if we look here, x, which is the straight line, and y is the dashed line. So x solidifies first, because you can see the straight line starts to go down before the dashed line. Okay, next one. A student argues that liquids X and Y are the same substance. State what evidence there is to support this, while they both freeze at the same temperature. So they both have the same freezing point. Okay, next question. A beaker contains hot water. The student wants to calculate the thermal energy lost by the hot water when she puts a cold aluminium block into the water. What information does she need to make this calculation? Well, again, this comes from our equation. So if we want to know the change in the thermal energy, that equals the mass times the specific heat capacity times the temperature change. When we look at this formula, we can see that there are three things that she needs to know. The mass, the specific heat capacity of the water, and the temperature change. And so therefore that's our marks. 1, 2, 3. Okay, next one. The volume of the aluminium block is 8 times 10 to the minus 6 meters cubed, and the density is 2,712 kilograms per meter cubed. Calculate the mass of the aluminium block and show your working. So we're going to use the equation density equals mass divided by volume. We want to work out mass, so we want to bring the volume over here, so that we're going to get density multiplied by volume equals mass, and then we need to substitute our numbers in. So the density was 8.0 times 10 to the minus 6 meters cubed, multiplied by the volume, which was 2,712, and if we work that out we get 0.02. Unit, well, our units that we use for density in this example would be kilograms, which you can see from here. Multiplying these and this cancels the meters cubed out, leaving us with our mass volume, our mass unit of kilograms. And then finally, after the aluminium block has been added to the water in 3.3, the temperature of the water increased from 5 degrees Celsius to 18 degrees Celsius. Calculate the amount of energy gained by the water, and there's the specific heat capacity of the aluminium. Show your working. So again, we know that the change in thermal energy equals the mass multiplied by the specific heat capacity multiplied by the temperature change. The mass we worked out in the question above was 0.02. The specific heat capacity we've got here, which is 0.9 times 10 to the 3, multiplied by the temperature change, well, it went from 5 to 18, so the temperature change there was 13 degrees Celsius, and if we work that out, we get 234. And because it's a change in thermal energy, our unit will be joules. So, I hope you did well on those questions, and I hope you found out how to answer any that you didn't know. Check out part 2 of our video when we are answering the second half of the particle model question booklets. Good luck and happy sciencing.